Let's talk about the normal distribution. Continuous variables sometimes have distributions that are bell-shaped. These variables are called approximately normally distributed variables. Because the shape is so common, we study these variables using the Gaussian distribution, which is also called the theoretical normal distribution. We're going to call it the normal distribution. There's a mathematical formula here. You don't need to know it. We're not going to use this formula at all. For each value of population mean and standard deviation, we get a different graph. The overall shape and placement of a normal distribution curve depends on its mean and its standard deviation. There are infinitely many normal distributions, but we're going to talk about how to relate them all to one particular distribution called the standard normal distribution. Some properties of the normal distribution. The normal distribution curve is bell-shaped, so it looks like a bell. The mean, the median, and the mode are all equal and located at the center. So we can see in these pictures over on the right, I'm going to take the first one where we have two distributions and the means are equal, but they have different standard deviations. In this case, the median and the mode are all equal to that mean. That also means that the normal distribution is unimodal. One mode. And that mode again is in the middle with that mean. We say the curve is symmetric about the mean. So the curve has the same shape on one side of the mean and on the other side. If we fold the graph at the mean, the two pieces of the graph would collapse on top of each other. Just know that it's the same on both sides of the mean. The curve is continuous. That's why we call it a continuous distribution. There are no gaps or holes in the graph. For every value of x, there's a corresponding value of y. We can draw the graph without picking up our writing utensil. This idea of continuous has a special connotation into calculus. So a little insert right here, statistics is built pretty heavily onto calculus. This idea of area under curves. But we can still do statistics without having to study the calculus part. We just need technology to help us do the calculus part, which is why we're using Excel and Google with some formulas that we're going to talk about in just a few minutes. The curve never touches the x-axis. As you can see in all of these pictures, we have the x-axis here along the bottom, and the curves start to follow it at the ends, but they never really reach the x-axis. This is a lot like an asymptote that you may remember from an algebra class where we talked about rational functions or hyperbolas, for example. Those have asymptotes. The total area under the normal distribution curve is equal to 1. Because it is a probability distribution. Just like with our total probability of a sample space being 1, or in our discrete probability distributions, the probability will all add up, all the probabilities will add up to 1. So we have that same situation here with our normal distribution as that continuous probability distribution. There are lots of different other continuous probability distributions, throwing it out there. We've seen the uniform and the exponential in our book. We're not going to talk about exponential at all in our class, but uniform is kind of nice because it's easy to calculate the areas. And remember that area means the same thing as probability. So I'm going to make that note right here. Total area, and probability are going to be interchangeable pretty much from this point out. This idea of drawing a curve and finding the area under it, or drawing or having a distribution and finding the corresponding probability for a given value. We're going to use these two words interchangeably. Back in chapter 3, we talked about the empirical rule. The empirical rule is coming directly from the normal distribution. If I'm within 1 standard deviation of the mean, 1 standard deviation away, there's about 68% of the area lying between the values 1 standard deviation away from the mean. 2 standard deviations away is about 95%. And then 3 standard deviations is 99.7%. And again, this is just coming straight from the empirical rule, but it directly relates to normal distributions. And that's what we had emphasized in chapter 3, that we had to have an approximately normal distribution in order to apply that empirical rule. So let's talk about the standard normal distribution. The standard normal distribution is a very special normal distribution. And that normal distribution has a mean of 0 and a standard deviation of 1. You can see that it's graphed here. We've got our mean here at 0. And then within 1 standard deviation of the mean, you can see a similar pattern as what's above that we just talked about with the empirical distribution. 2 standard deviations away, and then 3 standard deviations away is almost all of the area, or almost all of the data. Because we need areas for probabilities, and we don't have rectangles like for the binomial distribution or special formula, we don't have a table for probabilities like a discrete probability distribution. We have a continuous probability distribution. So all of the values here along the x-axis are represented in the normal distribution. To create a table would just be absurd. So we need other tools to find the probability / area under the curve. There are tables that exist for when technology wasn't as widespread as it is now. So you may be able to find standard normal tables on the internet. You may also see it in the very, very back of your book, of the online book. There are some links there to some standard normal tables, just in the event that if you wanted to check that out, you could. But I would strongly encourage you to take use of Excel and Google. They calculate using built-in functions. It does take a little bit of practice to make sure that you've got the right numbers in the right places. But hopefully the breakdown on the next page will be able to help you make sure those numbers are correct. So don't worry too much about those tables of calculations. Let's let technology do it for us. A couple of things to note here. We'll be looking at the Excel and Google formulas for both any normal distribution, where we have to input the mean and the standard deviation into the formula. And we'll look at the standard normal distribution calculation that's also built in. So Excel and Google have 4 functions that we're going to be able to use to find different things. Before we do that though, we've already talked about a z-score in chapter 3. This formula is exactly the same. The z-value is the same thing as the z-score. They mean the same thing. The z-value is just in context of normal distributions, how we can relate any normal distribution to the standard normal distribution. So the z-value, and unfortunately I didn't have this typed in, so I'm going to write it in. The z-value relates any normal distribution to the standard normal distribution. So we can take an x value from any normal distribution, and using this formula, x minus mu divided by sigma, we can relate it to the standard normal distribution. It can be really handy if we want to calculate this first and then use our standard normal functions, but we don't have to do that. I'm giving you the option in case you need it, and in case you're given a z-value and you need to find the probability corresponding to it, you have the standard normal functions. But most of the time when we're doing any normal distribution calculations, we're going to use one of the first 2 that are listed here on this page. So let's take a look at our functions. Excel and Google both use norm.dist, and then they ask for an x value the value where you want the distribution, the mean of the distribution, standard deviation of the distribution, and then cumulative for us in this chapter will always be true. We are never going to use the false in chapter 6. We always use true. So let's talk about this function. The Excel and Google description is pretty vague, so I'm making notes along the side, hopefully will help you. Excel and Google return the normal distribution for the specified mean and standard deviation. Function has a very wide range of applications. The notes that I've written though, given an x value, this function norm.dist gives you the probability to the left of the x value. So see that probability, also percentage, area, or proportion, all of those words here are being used interchangeably. But the idea is we are giving the x value to the function and it's returning a probability. Let's draw a picture to illustrate this. You're going to see me draw lots of pictures in this chapter too. Let's draw a normal distribution. We'll put the mean in the middle. Now, first off, the bar along the bottom, this is a number line, just like in algebra, and these are where the x values live. The actual values that we'll be considering. The x value would be the measurement that we would submit to the normal distribution. So if we're looking at, for example, heights of basketball players. We know in general heights are normally distributed, but let's say we asked what's the probability that a basketball player chosen at random has a height of less than 6 feet. So the 6 feet is the measurement that we would put into the normal distribution as x. Less than is to the left. So the smaller numbers are always to the left on the x value number line. And if we pick a value for x, like our example, 6 feet, then this normal distribution function will give us back the area to the left of that x value. So given an x, the function gives back the area. The area specifically to the left. This is important. We're not always going to be given a problem where we're asking less than. As we saw in chapter 5 with binomial distributions, we could talk about areas to the right, we could talk about greater than, we can even talk about between. And all of those are important, and we're going to see some examples in just a few minutes. But again, just pointing out, this formula returns area to the left of a given x value. Another function that Excel and Google will accept is norm.inv, or the inverse norm function. In this case, norm.inv returns the x value that corresponds to the given probability for the mean and the standard deviation. So this time we're giving the norm.inv function the area, and norm.inv gives us back the x value. So given a probability or percentage or area, norm.inv returns the x value on the standard normal. Ooh, on the normal, that's a typo. Sorry about that. Cross that out. On the normal distribution, so that the probability is the area to the left of x. And then we have the standard normal distribution. So the first two are for any normal distribution, and we can make a quick note of that. The next two are for only the standard normal. And unfortunately, these are split across 2 pages, but know that the first one and the next one on the next page are only for standard normal. So the first one we have Excel, norm.s.dist. Excel expects that cumulative notation again. And so we see that here. Cumulative, always use true, only for Excel. Google, however, we have two examples, one with dots and one without. Google doesn't really care if it has dots or not. But the big difference between these and the ones for any normal is we have this S in the middle. Notice up here in norm.dist, there's no S in the middle. So this norm.s.dist is for that standard normal distribution. So if we know we have a standard normal distribution, we can use this norm.s.dist. Or if we take the x value that's given to us and use the z value conversion, convert the x to z, then we can use the norm.s.dist. To draw an equivalent picture, this mean, though, since it's standard normal, we know we have a mean of 0 and a standard deviation of 1. We know we have a z value because we're on a standard normal distribution, so this norm.s.dist is going to return the area to the left again, to the left of the z value that we give it. So for standard normal, this number line on the bottom acts just like our x value number line above, except it's a z value number line. We're going to finish out only for the standard normal. Here we have norm.s.inv, and again the key here is that s in the middle. The inverse norm for the standard normal only requires the probability, not the mean and the standard deviation like the one before. So only use it for standard normal. Or we use this first to get the z value that corresponds to the probability we have, and then convert it to the x scale. We can either plug it into the z value formula and solve for x, or our book has a nice convenient rearrangement of the z value formula where we solve for x. X equals z sigma plus mu. It is easier just to use norm.inv though in the long run, and so that's what we'll do.